to our next session of our presenter talk, Lieutenant Colonel Technologies Insinyur Dr. Vikraswara Munikanan. He will deliver his presentation entitled Preparation to Chemical Weapons Blast Threats for Malaysia Defence and Security Agency. Please welcome Lieutenant Colonel Technologies Insinyur Dr. Vikraswara Munikanan.
Hi, very good day to all of you. Today, I'm going to discuss on the preparation to chemical weapon blast threats for Malaysia Defence and Security Agencies. One of the important topic that currently that we need to highlight, and also we have to get prepared. All right. So the Tokyo subway sarin attack in 1995, March 20, is an example to show how the chemical weapon could be used in the public by terrorists or radical group. So this actually a chemical blast terrorism that can illustrate the diversity of disciplines and perspectives required to confront these threats, whether naturally occurring or purposely caused. So normally the response to chemical blast terrorism is an important agenda in Malaysia. And also, according to the LEDGuard, the risk of facing chemical warfare agents, terrorist threats is higher during these days. So the use of chemical agents, especially increasing attraction among the terrorists due to the easiness in production and dissemination. Is very easy to purchase or easy to get and easy to produce. So the effect of using this material in small quantities alone can have a severe impact. So we may seen various incidents outside Malaysia, other countries especially, to the incidents we know, like such as in Japan, right? Chemical weapons now are grouped together with fission and fusion weapons, which we call as weapon of mass destruction. That's why this is prohibited in many countries. All right. So this object, the paper will focus on two main aspects, which is to gain understand or to gain the understanding of the Tokyo sarin attack, and will try to simulate if similar situation may occur anywhere in Malaysia as a precaution step, and also to study the various points of view related to this cooperation between the national agency, standard operation procedure, blast threat defense, and also even to see the source of CWA's ingredients that available in Malaysia. All right. As a method of this study is through the primary sources of unpublished official documents from the government officers, from civil and military source, of course, and also through the interviews. And the secondary source is through books and official document publications, working papers, presentation, and speeches, and academic journals. Through the findings and through the review, we find that the threat to public order may originate from racial and communal issues, religious issues, political agitations, economic issues, educational issues, industrial disputes may occur, may increase the threat to the public order. All right. So in this situation, the preparation for CWA threat is important. All right. So we have many acts, legislation that can be used to counter the threats. Okay, actually, we have many, and few of them are listed here, such as the Penal Code as 141, the Police Act 1967, the Public Order Act 1958, Industrial Act 1967, Educational Regulation 1959, and Explosive Ordinance 1957, the Protected Areas and the Protected Place Ordinance 1959, the Arms Act 1960, Fisheries Act 1963, Internal Security Act 1960, and many other acts or legislation that available in Malaysia. All right, this actually as a protective source, as a protective source for us to counter this kind of blast terrorism. All right. Next, what are the possible approach for this kind of incidents? Okay, basically we can see that the chemical weapon terrorism can be encountered by 8 types of response, namely, first, of course, we need awareness to be created. Next, we need to be prepared with the laboratory, preparedness, all right? So, and of course, number 3 is plan in place. We have to have a good plan that we can use for this kind of incidents. Individual and collective protection. This, of course, we have to get prepared with the PPE. And detection and characterization with the equipment and so on. And of course, the emergency response with a plan and proper management, of course, on the emergency response measure to protect the public's health and safety, and of course, the treatment and safe practices through the health and also defense, right? Next, we may also have proven modern technology and equipment that can respond successfully and with the modern education management principles such as training needs analysis, operational research that can support this task. And also, we also may have simulation software such as training and planning platform that offers a repeated control and advanced evaluation of the CWAs, disaster in some of the developed countries. Integrated, standardized the curricula to meet the first responder respectively. And also we need the apex agencies such as National Security Councils and Defense Research and Development Organization can support and take serious measures on this agenda. The standard operating procedure also can be part of the consideration because each agencies have their own SOPs to face CWAs. The NSC should come out with a single SOP within all agencies that involve CWAs to make sure we have some language on how to counter the CB at this part, and continuous action can be taken. These are the few incidents that happens in Malaysia. These are accidents. This may also can become a terrorist threats to us in the future. May. All right. So therefore, we need to take a serious precaution on this. All right. In Malaysia, the planning, preparation, and response to chemical weapon terrorism involve many parties. Yeah. First of all, of course, the National Security Council, the Malaysian Armed Forces, internal security forces such as police, Ministry of Health, okay, then other related agencies. Throughout the response, these agencies use their protective action guidelines, which may be their SOPs in each agencies. There is also perceived need to integrate and standardize the curricula to suit the respective first responder. All right. As a conclusion from my paper, it is strongly felt that with the able support agencies like NSC and guidance from the Defense Research and Development Organization, the training effort in chemical weapon agents, disaster management will get the right impetus to achieve a stature of modern, progressive, and mature and durable. I think with that, I would like to thank all of you for listening to my presentation. Thank you. And in the future, we may meet again with some other related topics. Thank you very much.
Thank you to Lieutenant Colonel Technologies Insinyur Dr. Vikreswaran Munikanan for a very interesting presentation. Moving on to the next presentation, I would like to invite Brigadier General Professor Insinyur Dr. Nur Azman Muhammad Nur to present his project entitled Explosive Blast Test on Scale Model of Ammunition Storage Facility. Please welcome Brigadier General Professor Senior Dr. Nur Azman Muhammad Noor.
Assalamualaikum warahmatullahi wabarakatuh, and greetings to our panel of judges of Symposium on Blast and Impact Resistant Materials for Civil Engineering for the year 2021. Our research title is Explosive Blast Test on Scale Model of Ammunition Storage Facility. This is our list of researchers: Nur Azman Muhammad Noor, Ahmad Mazlan Osman, Salahuddin Ar-Rumat Sumadi, Arifin Ismail, Muhammad Alias Yusuf, Rizbi Suhaimi, and myself, Muhammad Shakir Sharani. We go to the introduction of our research. What is Explosive Safety Quantity Distance, or ESQD? ESQD referred to the minimum safety distance to public access area to an ammunition depot. The safety distance means to protect life and property against the blast wave, shock, and fragment projectiles. Thus, such a safety distance required a large land area as a buffer zone. The major deciding factor in specifying the safe distance of an explosion is the throw-out distance of flying fragments or debris caused by the explosion. If the explosive in one of the bunkers exploded, that particular bunker will be blown up into pieces. Pieces and chunks of concrete will be thrown outwards as projectiles that threaten life and property. In most instances, blast incidents, the major fatalities on humans do not come from the blast overpressure or shock wave, but due to the flying of falling building debris like glass and rubble. This research aims to conduct a scaled-down field blast test on structural models made from foam concrete and normal concrete. Then we compare the performance of both materials in terms of their blast debris and blast debris properties like the debris dispersion, throw distance, size of debris, and weight of the debris. Our main objective of this research is to study the suitability of foam concrete as an alternative material for the construction of the blast-related structure in reducing the blast debris throw distance. With the reduction in blast throw distance, the buffer safety zone around a potential explosion site can be reduced. This research involved three main activities: preparation of scaled model structures, field blast testing, and analysis of results. The focus will be on lightweight foam concrete, explosive safety distance, characteristics of blast debris, and methods of conducting blast debris analysis. Two blast tests for lightweight and normal concrete of different densities were conducted. The blast tests were recorded using a high-speed camera. Blast debris is collected and mapped using sector markings. Debris data are recorded, analyzed, and reported. The focus of the research is comparing the performance of both materials in terms of blast debris, throw distance, size, and weight. Blast effect on structures. An explosion will create a blast wave. The shock wave is the primary damage mechanism in an explosion. The pressure it exerts on building surface may be several orders of magnitude greater than the loads for which the building is designed. The shock wave will penetrate and surround a structure and acts in direction that the building may not have been designed for. In terms of sequence response, the blast first impinges on the weakest point in the vicinity of the device, closest to the explosion. The explosion pushes on the wall and causes wall and door failure. As the shock wave continues to expand, it pushes both upward and downward, causes maximum failure to the structure. We can see the example. We can see the blast shock wave is reflected on the ground and affecting the shelter. This is our example of air burst. blast debris field study. From the literature, several trials have been carried out to determine the debris generated by explosion inside test structure. From such trial and accidents investigation, improvement to the safety standards have been made. A NATO bibliography of reference relating to explosion-produced debris contains over 475 entries, dating back over 45 years. However, comparative study on blast debris between lightweight and normal concrete are not known been done or published. It is important to determine the tolerability level and minimize the risk of blast effects on personnel and property. This requires more understanding of the effects and consequences of blast effects, especially the effects due to the debris distribution. The impact of debris on personnel and property is dependent on the debris mass, velocity, material, shape, number, and impact location. Fragment and debris cloud that is projected into field around the explosion site is complex and not readily calculable. To quantify these effects, it is necessary to perform modeling and field testing. Knock et al. In 2004 tested the behavior of masonry debris on impact. They found that post-impact velocity is predictable using simple empirical formulae. Then the impact behavior of cube is like sphere debris subject to types of impacted surface. In an ideal world, a complete detailed description of debris distribution in terms of mass versus velocity versus debris number is needed as a function of distance from explosion center. However, this is usually not achievable in practice due to time and or cost constraints. What may be achievable are the measurement of mass versus the number of debris versus range or position, and estimate of the distribution of initial velocity. The prediction of velocity time histories of individual debris pieces is at best conjectural due to the indeterminacy of initial velocity, the randomness of shape, which is the drag, and the effect of ricochet, roll, and bounce. The objective, therefore, must be to achieve the best information practicable to describe the debris distribution. This is our selection process of scale model parameters. The finding of this research is not limited to the single kind of structure, but the study also selected a typical explosive storage bunker as the subject specimen. The major interest of blast debris distribution study is concerning the ESQD, which is the safe distance of explosive storage bunker. Based on the shape and size of actual standard 13 meter times 13 meter of explosive storage bunker, a balance of various factors like ease of transportation and handling, required weight of explosives charge, available testing range and safety aspect. We select 1/16 scale of model was selected. The overall size of the 1/16 scale explosive bunker is 0.9 meter by 0.9 meter and 0.5 meter high. This size is suitable for easy handling and transportation. The total weight is between 180 kg to 250 kg. However, the thickness of shell and wall was scaled to 1/10 to avoid having a very thin structure. Features like the front and rear vent and steel door openings are provided so that the blast simulates the real behavior of storage bunker. The magnitude of blast load suitable explosive charge weight. This is small scale blast test. An adequate amount of type of explosive are needed for the total demolition and disintegration of the test sample. A suitable type of explosive material will be selected for the test to meet the goals of the experiment. Preliminary computation using SBEDS, single degree of freedom blast explosion design software, indicates that 0.82 equivalent TNT of bare explosive is sufficient enough to disintegrate the model structure. However, the software does not detail the level of failure that could happen. The failure mode was based on the rotation angle and ductility response. with the same amount of explosive using conweb software, it indicates that in terms of peak overpressure, an area of 150-meter radius is sufficiently safe to conduct the test. The peak incident overpressure drops to about 2 kilopascal within about 40 meters. However, considering blast fragments that can go much further, a minimum safety radius of 300 meters should be provided. The preparation of test specimen. In total of 4 test specimens were cast, 2 numbers of lightweight concrete of different densities, and 2 numbers of normal concrete density. The preparation of the specimen were per the standard construction practice of British standard. Before the casting, some trial mix was conducted on available data from records to achieve the target strength of 20 Newton per mm square. Preparation of the foam with the correct ratio between water and norate protein-based foaming agent using a portable foam generator. A different color cement was used for the different densities of the concrete so that the blast debris collected can be differentiated from the different test specimen. Test specimen 1 using the ordinary Portland cement, we use the color gray. Test specimen 2 using the green colored cement, and test specimen 3 using red colored cement. Test tube cast and test for 7 days and 28 days compressive strength to monitor the strength of the cast specimen. Blast sequence recorded by the camera. This the first picture is before the blast. The second one is upon detonation, and the third one debris projectiles. We can also see the fourth one, which is the scene at ground zero, half a second after the detonation. The dispersion pattern of debris. The dispersion of the debris depends on its location concerning the radial hemispherical blast wave. The blast debris was projected radially from the location of the explosive charge. The debris projectiles depend on the mass of the debris, which influence the debris initial project velocity. The throw distance depends on the angle of trajectory and debris initial velocity. Based on the angle, trajectory, and mass of the debris, as shown in the figure, the pattern of the debris dispersion should be as at close range. The debris size should be more of the small size compared to the bigger size, and at mid range, the debris size should be contain a balance of all size, and at far range, the debris size should be more of the bigger size. From the data collected, it was confirmed that higher density material projected further than lighter material. Based on the figure shown, on average, the heavier material recorded on average, biggest piece in the sector is at 195 grams, while the lighter material is at 138 grams only. While for the median, the heavier material recorded at median of the biggest piece in the sector is 91 grams, while the lighter material is at 60 grams only. To conclude our research, the test proved that throw distance is dependent on the mass of debris and trajectory angle. Bigger size debris is found at 2 groups. One at a closer distance, which is 18 meter to 66 meter to impact point, considered from those in high trajectory, and the other group at far distance, which is 180 meter to 220 meter. Assuming low trajectory, as illustrated in the figure before, bigger size debris from normal concrete, which is the higher density, exhibit bigger composition at far range. This proved that with the same angle of projectiles, higher density concrete, due to its bigger size and surface area, subjected to bigger impulsive force, thus pushes to a further throw distance. The research achieved the expected result in terms of blast debris safety distance requirement. Foam concrete also can be used as an alternative for the construction of bunker, where foam concrete, which is the low density concrete, performs better than normal concrete in terms of safety distance requirement. That is for my presentation today. Thank you.
Thank you to Brigadier General Professor Engineer Dr. Noor Azman Muhammad Noor for a very interesting presentation. Moving on to the next speaker, Engineer Suryadi Sojipto. He will present his project entitled Preliminary Investigation of Steel Plates Protected with Gypsum Boards Subjected to Explosion. Please welcome Engineer Suryadi Sojipto.
Assalamualaikum. Okay. Without further ado, I would like to introduce myself. I am Suryadi Sudipto, Senior Lecturer from Faculty of Engineering, National Defence University of Malaysia. Today, I am going to present our research finding on the preliminary investigation steel plate protected with gypsum boards subjected to explosion. The common practice in the steel construction is to incorporate the steel beams and columns with protective system, such as fire protection. Some of these protective systems, in example, intermissile coating, do not have any energy absorption ability. Therefore, the effect of explosion are directly and completely imposed on the steel structure. Owing to that, most of the researchers will neglect the influence of fire protection materials to the effect of explosion. However, some systems, such as fire protection system in which boards are used, there is some space between the fire protection and the steel structure. The protective system may have some energy absorption capacity to reduce the effects of explosion on the steel structure. The aim of this study is to investigate the behavior of steel plate protected with gypsum board subjected to explosion through experiment. Now go to methodology. The material used are mild steel plates, S275, 9 pieces of it. The plate dimension is about 500 mm times 500 mm and 3 mm thickness. The exposed area is about 300 mm times 300 mm. For gypsum board, we use impact resistant board, which is 19 mm thickness from USD borer, and each sample will be subjected to explosion from 10 grams of plastic explosive bomb. And the testing location is at the Camp Concoy Negeri Sembilan, one of the UPNM facilities. Now the testing was categorized into 3 cases, which are case 1 involved only steel plates. This was going to be control sample, and we're going to compare with case 2 and case 3 to the case 1. Case 2 is consists of steel plate with a gypsum board, and case 3 for steel plate with gypsum board with gap. Okay, the case 2 and case 3 is to study the difference between 2 methods of fixing the boards to the steel structure, as can be seen in this figure at the bottom right of the slide. One of it is there is a gap between the board and also the steel structure, and the other one is no gap. So this type of fixing boards to the structure, we're going to analyze and to study which one is the best that can give some protection from explosion. This is the test setup, the complete test setup for the blast test. The explosive port, this is the explosive PA4, hanging 1.5 meters from the ground and 1 meter apart from the center of the steel plate. And at the back, strain sensor are glued to the back of the steel plate and connected to high-speed data acquisition system in order to measure the deflection. This is the side view of the case 3 setup. As you can see here, this is the white color is the void and steel plate and gypsum board. So the difference is between case 1. Case 1 only we have steel plate, and case 2 we have steel plate and gypsum board without gap, and case 3 we have a steel plate, gap, and gypsum board. This is to simulate the two fixings method for gypsum board to the steel structure. Let's watch this test video recorded with phantom high-speed camera. The speed of the video, the speed of the camera actually can capture 25,000 frames per second, but I reduce it to 3,000 frames per second. If not, it's going to take a long time to finish that recording. You can see the blast wave clearly propagated toward the steel structure. This explosion is taken about microseconds, and you cannot see in the naked eye. If you can watch in the videos, this is from the high-speed camera that can take 25,000 frames per second, and we can see that the blast propagate to the sample. Okay, from the so this is the table shows the average of the result obtained from the field test. 8 of these can be seen that this on board reducing the deflection of the steel plate here when subjected to explosion from 4 mm for case 1 steel plate only, to 2 mm when we protect with gypsum board, and 1 mm reduced to 1 mm if there is a gap between the plate and also the gypsum board. The deflection of the plate was measured using ruler. This is because the strain sensor we attached at the back was detached from the steel plate, okay, and does not give good result because of the high heat and also the explosions, the blast wave. The glue cannot withstand, and the strain sensor detached from the steel plate, and it does not give good result for us. Now, from observation, the gypsum board in case 2 does not have any damage at all. Okay, when there is no gap between the board and also the steel plate, the boards are good in resisting the compression force, but not in the tension. The tensions was provided by the steel structures. Compared to case 3, the gypsum board had been heavily damaged. You can see clearly cracks at the middle of the board, and the cracks occurred can reduce the fire performance of the gypsum board. However, it gives the best protection or absorption capacity and can protect the steel plate from deflect. As for conclusions, this work was devoted to assess the behavior of steel plates protected position board when subjected to explosion. It was found that both types of fire protection, such as gypsum boards, does have energy absorption capacity to reduce the explosion effects to the steel plate. Protected steel plate with gap, which is case 3, gave the best performance when subjected to explosion. However, the gypsum board have been damaged, and there needs to be further research to study their fire performance. The overall findings in this study suggest that both type fire protection does have energy absorption capacity to reduce the effect of explosion on steel structure. We would like to gratefully acknowledge the financial support given by the National Defence University of Malaysia and the short-term research grant. With that, I conclude my presentation. Thank you. You may contact me through this email, suryadi@upnm.edu.my. Thank you very much.
Thank you to Insinyur Suryadi Subjekto for a very interesting presentation. The next presenter is Major Madinah Jaafar Mat Arif with her presentation entitled Statistical Approach to Predict the Velocity of Detonation for Immersion Explosive. Please welcome Major Madinah Jaafar Mat Arif.
Assalamualaikum and salam sejahtera. I'm Major Madinah binti Jaafar Ma'arif. I'm gonna present for this symposium the paper with the title Statistical Approach to Predict the Velocity of Detonation (VOD) for Immersion Explosive. The objective of this paper is to obtain the best formula for the new immersion explosive by using the statistical approach. Introduction. Explosive is high energy material which contain great amount of potential energy. There are two classifications for explosive, for civil and military use. Explosive for civil use such as immersion explosive, slurry explosive and N4, amino nitrate, fuel oil are ammonium based. The velocity of detonation (VOD) of explosive for civil use is range from 2,500 to 7,000 meter per second. And the civil explosive has low reaction rate compared to high explosive, and it well known as non-ideal detonation behavior. For military purpose, usually need the VOD within 4,500 to 11,000 meter per second. In this research, we focus on development of immersion explosive. Immersion explosive, the performance of the explosive can be determined by velocity of detonation or VOD. Oxidizer, fuel and sensitizing agent are the common formulation. This table shows the ingredients for oxidizer phase, fuel phase and sensitizing agent, and also the percentage. This is the common formulation. So the basic equation for immersion explosive is 1 mole of ammonia will produce the carbon dioxide and water also the nitrogen gas. The method for this paper is first is data from the field blast test, and number 2 is multiple regression analysis from SPSS. The method 1, data from the field blast test. There are 20 mix of immersion explosive. Each mix have 3 samples, and then the range of oxidizer used were between 60 to 79%, water 15 to 21%, and sensitizer 1 to 4.5%. And then monitoring VOD using the fiber diagnostic methods. The second method is multiple regression analysis, SPSS. So the version is SPSS 16. The regression equation describe the subsequent form as shown below. Y equal to Y, the dependent variable, equal to negative beta naught, the constant, plus beta 1 x1, the independent variable, plus beta 2 x2 and another independent variable. After determining the variable involved, analysis was conducted. Correlation tests are conducted to analyze and elaborate on the relationship between the variables that exist. The regression coefficient value R2 also determined during the analysis. So this is the analysis result. So this result is from the correlation analysis. From here we can see that oxidizer 1 and oxidizer 2 has a very strong correlation because we can see here the value is negative 0.738. In this correlation, the significance is at 0.01. And then also the sensitizer have the correlation with the oxidizer 1 and oxidizer 2. However, the fuel was omitted from the analysis because it did not show the correlation since it is constant variable. So this is the coefficient table. So we can, from the coefficient table, so we can get the value for the formula. So from here we can see the constant is minus 6866.187. The oxidizer 1 is 618.301 and sensitizer is 435.087. This is the graph for the coefficient that show the close relationship between the dependent variable and independent variables. So the result from the analysis, coefficient regression R2 is 97.5%, which this model has the influence factor towards the model or the formulation. This means that the confidence level for this formulation is 97.5% accuracy. And then from the straight line of the regression analysis model, the optimal VOD can be determined by using the formula below. Y, the VOD, equal to minus 6866.187 plus 618.301 times water plus 435.087 times sensitizer. The conclusion, the formula obtained from multiple regression analysis show strong relationship between independent and dependent variable. This research provides that formula-based and common metric composition with regard of some different ingredient as it based on local products. So only that from me. Thank you.
Thank you again to Major Madina Jaafar Mat Arif for a very interesting presentation. Moving on to our last speaker for this afternoon session, let's welcome Brigadier General Professor Insinyur Dr. Noor Azman Muhammad Noor to present his project entitled Exposure Impact on Movable Targets. The session is yours.
Assalamualaikum and salam sejahtera. Hi, I'm Nuzaitul Zulkifli. I'm a team member of this project, Explosion on Impact on Movable Targets. This project is led by Brigadier General Professor Insinyur Dr. Noor Azman bin Muhammad Noor. Okay, as we all know that the blast impact from the external explosion can cause a very bad damage to the structures and also can cause a badly injury to the publics. And now the use of explosive by terrorists has become a universal phenomenon in certain parts of the world. So in order to increase the protection for the public, we need to study this blast impact so that we can create something to protect us. Okay, the explosive has been widely used in the military application for demolition of enemy installations and or defense positions. They are also being used to obstruct and or to create the obstacles to the approaching enemy. But in non-military environment, the explosive are widely used to assist the earthwork, especially in the rocky areas, and the explosive also being used to demolish all or unsafe structures to give way to new development. The objective of these studies are: first is to scrutinize the fundamentals of blast and related literatures on explosive blasts. The second one is to investigate the blast force as a third and its impact, theoretically and experimentally. And the third one is to analyze various methods of testing and measuring blast impact. So, this study will focus on creating a better understanding on the fundamental effects of explosion, such as its behavior and consequences. So, this will include we need to analyze the strength of the blast wave relative to the distance and the physical responses to the explosion. Okay, this is the methodology that we use for this experiment, which involve the three main activities. That is, first, we need to identify the common explosives available, and in this experiment, we use four types of explosive. That is, number one is trinitrotoluene, as known as TNT, and plastic explosive number 4, PE4, composition C4, and the pentaerythritol-tetranitrate, that is PETN. Okay, and then we do the experimental setup where we're preparing the sample as a target for the blast testing. So the main target to be utilized include the 500 cubic millimeters of the steel box and on a steel plane, and then the secondary targets, which include the concrete samples and the brick walls. And then the blast test will be conducted with various intensity from 200 grams to 1000 grams and at the varying distances. So the related data in terms of the displacement of the target will be collected, and we do the result analysis. Okay, this figure shows the blast wave of the airbus. The airbus will create the incident shock front. Then you can see the incident shock front is the first wave that travel and then come the reflected shock front, where the reflected shock front is more higher intensity than the incident shock front. And then the combination of the both shock wave will create the march stem, which is a parallel to the ground, and march front, perpendicular to the ground. The march front is the wave that go to the target and will destroy the target. Okay, this is a blast wave surface burst. Okay, this figure shows that the ground reflected wave from the surface burst, which is a combination of initial blast wave with the reflected wave. The wave front will damage above ground target, such as the shelter shown. Okay, this is a graph pressure versus time. The air pressure created by the explosion will reach its maximum level in split second and will also dissipate in a very short time. So the blast pressure will go down to the negative pressure before going back to the normal atmospheric pressure. Okay, this figure shows that how we set up our experiment, and as you can see here, the explosive will be placed on the timber peg, and the target, a steel box, is placed on the steel plate with known as a friction coefficient acting as a friction rail for the target. So the explosion will cause the displacement to the target due to the pressure exerted on the target. So both the displacement and the pressure is a variables that we need to be determined. Okay, this is the video that have been taken during the blast test.
Berarti waktu saya yang sampai ke break 50 pieces.
See how they measure the displacement.
585 mm. Specimen was not break. Specimen number 23 is not break by 500 gram explosive. C4 200 gram. The box has moved.
From the blast test that we have done, this is the data for TNT. And this is a blast data for PETN. This is data for composition C4. And this is the data for PE4. Okay, now from the tables and graph that I've shown just now, we can see that the normal trend of the high pressure due to explosion at closer distance, and there is a drastic reduction when the explosion is moved further away. So even though the most of the tests are classified as far detonations, we can see that when Z value is closer to 0.4, for example 0.5, the displacement of the target is big. So this shows the validity of the Z value as indicator of high impact area. And now this is the table that shows the ratio of equivalent displacement between several types of explosive relative to plastic explosive number 4. That means it's a PE4. So for conclusion, we can say that from the experiment that we have conducted, we found that C4 is the strongest of the 4, followed closely by PETN. PE4 is about 40% weaker than the two, C4 and PETN, while TNT is only about a quarter of PE4 strength. So it means that from the experiment that we have done, C4 is the strongest one, followed by PETN, and then PE4, and the last one is TNT. From this, the engineers and planners could use the data as another input for possible imposed load to provide a better design or protection against any act of terror or accidental explosion. So for the future research, since the amount of explosive that we use for the experiment is not more than 1000 gram, and the distance to the target were less than 2.5 meters, so it is suggested that a bigger amount of explosive and a greater distance to target are to be tested in the future research. So the data will be more meaningful in order to study the impact behavior of explosion on targets and vicinity. Okay, this research will further lead towards future research on structural design subjected to blast impact and structural response to weapon or blast effect. That's all for now. Thank you very much.
Thank you to Brigadier General Professor Insinyur Dr. Noor Azman Muhammad Noor for a very interesting presentation. Ladies and gentlemen, with the last presentation, it marks the end of our presentation session.
Our closing ceremony will begin shortly. On behalf of all the committee members, we welcome the distinguished guests, ladies and gentlemen, to the closing ceremony and best paper and presentation for Sbirmce 2021.
Bismillahirrahmanirrahim. Thank you, Mr. Azizi. Assalamualaikum, ladies and gentlemen. Now, I would like to announce the Best Presenter and the Best Paper Award for Sbirmce 2021. For the Best Presenters, award goes to Paper ID BIM 21102 entitled Numerical Analysis of the Response of Reinforced Concrete Panel Strengthened with Biomass Electrometric Polyurethane Coating Under Blast Load, presented by Associate Professor Sudarshan and Rahman from Monash University, Malaysia. The second Best Presenter Award goes to Paper ID BIM 21103 entitled High Tensile Bollard for Blast Loading Using Composite Concrete, presented by Associate Professor Technologies GS Dr. Muhammad Azan Yahya from University Pertahanan Nasional Malaysia. For the Best Paper Awards, the winner goes to Paper ID BIM 2111 entitled Influence of the Jute Fibers in Dissipating Energy Caused by Impact Loading on Reinforced Concrete by Mr. Shehab Ahmed from Capital University of Science and Technology, Islamabad, Pakistan. The second Best Paper Award goes to Paper ID BIM 21106 with entitled Effect of Fire Insulation Material on Cable Action of CFRP Plated RC Beams Under Evaluated Temperature by Professor Insinyur Dr. Raizal Saifulnaz Muhammad Rashid from University Putra, Malaysia. Congratulations to all the winners and thank you to all participants for your contribution for this symposium.
With that, our Sbirmce 2021 is officially ended. On behalf of the organizer, we would like to seek apology for any mistakes during this symposium. We would also want to thank each of you for your participation and involvement throughout this symposium. We hope to see you soon again, hopefully in real next time. Until then, thank you and Assalamualaikum.